Recording is now started. Welcome to anyone who's watching this online. Now I will open up the floor to questions. Anyone have any burning questions about this? We are covering sections. We are covering sections 2.1, 2.2, and 2.3. So we've got instantaneous rate of change, the derivative is a function, and then interpretations of the derivative. So this is kind of us getting into the actual meat of calculus. If there are no questions, then I will just start going ahead and doing some practice problems. Okie dokie. So we are going to start with doing section 2.1 practice problems. We're going to go ahead and start with number 2. And this, by the way, is on page 95. That's where I am. Sorry, let me get my screen rearranged a little bit here. All right. All right, so question 2, use the graph in figure 2.7 to decide if each of the following quantities is positive, negative, or approximately 0. Illustrate your answers graphically. So part A says the average rate of change of f of x between x equals 3 and x equals 7. The graph in figure 2.7 is going to look something like this. All right, we've got this low point here at 5, and this is okay. So that's about what figure 2.7 looks like. And now we are trying to decide if the average rate of change between x equals 3 and of f of x between x equals 3 and x equals 7 is positive, negative, or approximately 0. So how do you think we're going to do that? Feel free, if you have any thoughts or suggestions, just to put it in the chat box and we'll talk it through. Slope, yep. What we're going to do is we're going to pick out this point, which is going to be f of 3, and this point, which is going to be f of 7. And the average rate of change is just going to be the slope between them. So that is going to be positive. So the answer to A is the average rate of change. Positive. All right, what about the instantaneous rate of change at f of 3? So we're right here.
It would be negative?
Yes, it is going to be negative. And why is that?
Because it's decreasing?
Yep, right at f of 3. If we go to like f of 3.1, it's going to get smaller. And so f of 3 is on its way down. So right at f of 3, the instantaneous rate of change is going to be negative. Okie dokies. Why don't we try problem 4? Okay, so in time of t seconds, a particle moves a distance of s meters from its starting point, where s is equal to 4t² plus 3. So we have this equation, which I'm just going to write out so that we don't lose track of it. And S is going to be distance. And it's a function of time. And that's kind of important to know. Something that I've seen a lot in calculus classes is the relationship between distance and velocity, or displacement and velocity, and then velocity and acceleration. So basically, what that is velocity, which is what part A is going to be asking us for. The velocity is the rate of change of the distance. And so that's something that they're going to use, like, language-wise, that might not be entirely clear. But if you see something that says, so you have a particle and it's moving a distance, and then they want you to find the velocity, what they want you to consider is the derivative or the rate of change. So this is asking for average velocity between t = 1 and t = 1 plus h. So what it's asking us to do is to find the average rate of change. So this is part A. It's asking us to find the average rate of change between, in part A1, is going to be between S of 1 and S of 1 point, or rather 1 plus 0.1. So let's go ahead and do that just to start with. We're going to do basically the exact same thing that we would do with like what we did up there. We're going to figure out what S of 1 and S of 1.1 are going to be. This time we're not looking at graphs, though. We're looking at numbers. So S of 1 is going to equal 4 times 1 plus 3, which will be 7. And S of 1.1 is going to equal 4 times 1.1 squared plus 3. Let me grab a calculator and we can figure out what exactly that is. So that's 4 times 1.21 plus 3. So the answer is going to be 7.84. Okay. So we know that S of 1 is going to be 7, and S of 1.1 is going to be 7.84. I think the easiest way to kind of visualize it is to like kind of sketch out a little bit of a graph and say this is 7 and this is 7.3. So we have 7.1, 7.2. 7.1 is going to be, wait, no, I mixed up my axes. Don't feel afraid to like call me out if I do something stupid like that and swap axes. So here we have 1, here we have 1.1, here we have 1.2. And we'll just do 7, 7.2, 7.4. So at 1, it'll be about 7. At 1.1, it'll be 7.1. So you can see that there's a positive slope, positive relationship between the two. I have a tendency to relate things back to graphs, especially when talking about this type of stuff, just because it makes it easier for me to understand it. But if you can just look at that and be like, yeah, that's positive, absolutely, then yeah, go ahead and do that too. So yeah, so there's part 1. Now we are going to do part 2, which is asking the average rate of change, this time between s of 1 and s of 1.01. So again, we're just going to do essentially the same thing. Go back to our calculator. We know that s of 1 is equal to 7. S of 1.01 is equal to, let's see, so that's 1.01 squared times 4 plus 3. So this is going to equal 7.0804. So we're just going to call that 7.08. And so what we're going to do here, we again have a positive relationship between the two. Here, our average velocity is going to be, is the slope between these two more positive or less positive? What do you guys think?
I think will be more positive.
Okay. Let's just kind of sketch this out a little bit on a graph to kind of see what we're looking at. Here at 1, this is our point S of 1, right? This is our S axis, and this is going to, no, that's wrong. This is our T axis, and this is going to be our S axis. So this is the point S of 1, which is equal to 7. And then we have 1.1 right here, which is equal to 7.8. So our average rate of change here looks like that. On this one, though, we're looking at a point that's right here, and then a point that's about right here. I'm not so sure if that's the most accurate way of putting this, actually. So what we're going to do is we're just going to find the average between these 2 points to figure out exactly which one is more positive and which one is less positive. Because the way that I drew this, it's not very clear. Unfortunately, I should have just drawn a bigger graph. So the difference here, averages, we're looking at delta, the change in, oops. We're looking at what is the change in the y and what is the change in the x, right? And the change in the y here is going to be 0.84, and the change in the x is going to be 0.1, right? Because we're going from 1 to 1.1. And then here it's going to be 0.08 over 0.01. So these look like they're going to be about the same. But one is going to say, this one is going to say that the average rate of change is 8.4. And this one is going to say that it is 8. Yes. The point I was trying to make, though, is that they're very, very close. Like it's not discernible on the graph. And the fact that this is more precise. If we were to extend this decimal point out further, it would be 8.04. So this number is larger than this number. So what do you think is going to be the case with number 3? where we are comparing s of 1 and s of 0, 0.
Oh, it's going to be less positive.
Yes, it is going to be less positive. What number do you think it's going to be really close to? Like what, in terms of, have we talked about limits yet in this class? I don't think we have. So this is kind of a little bit of language that you haven't heard yet, but we're going to say it's approaching this number. So it's going to get really, really close to the number 8. So what we're going to do is I'm going to plug this into my calculator really fast. And I've got to type it right, so I have to retype it. So this is going to be s of 1.001 is equal to 7.008004. And so our average rate of change is going to be the difference between s of 1 and s of 0.01. So we have delta y divided by delta x. And so that is going to be, you can plug it into your calculator if you want, but it is going to be 8.004. So it's getting closer and closer to the number 8 as the distance in our x values get smaller and smaller. All right. So part B is pretty simple. Use your answers in part A to estimate the instantaneous velocity of a particle at time t is equal to 1. What do you think our instantaneous velocity is going to be based on these average velocities that we've calculated? Sorry, this is where my chat box was, so that's why there's always a big gaping hole here. So I'm going to move the chat box so I can fit this all on one screen. So our instantaneous velocity is what? Eight. Yeah, sorry, somebody said it in the chat room. Yes, 8. Nice. Cool. All right. So let us do, let's do problem 12. Oh, one sec. Do you have a question or did I do something wrong? Yes. What about the instantaneous velocity? No. The instantaneous velocity is not going to be, we had just had a comment in the group chat, so I'm going to, actually I'm just going to use an eraser so that I have all of this work down below. That is just going to be what it is at f of, or s of 1. In this case, s of 1 is 7, not 8. And what that is going to represent is the distance at time t, right? Because s is a function for distance. Yep. So actually what we're doing here is we're estimating the derivative. We're estimating the instantaneous rate of change. And later on, you're going to see how exactly you can take a formula like this and get a derivative function out of it. It's not something that you can do right now. So what we're doing is we're estimating it using average rate of change. So s of t gives us a distance. V of t the derivative of s of t, will give us loss. All right. Let's do problem 12. Do you guys all have your books with you? Sweet. So you guys can see problem 12. This is on page 96. What it gives us is a list of slopes and a graph with a bunch of points on it that is figured 2.14. And it asks you to match the slope to the point. So I'm going to have you guys do that for me. Just a tip. I typically figure out which one is 0 and then figure out which ones are positive and negative, and then I kind of go from there. That's kind of the order I take it at, because 0 is the easiest one to pick out. And so while you're typing, I'll just kind of sketch out the graph for anyone who doesn't have it. My tablet. Ah, looks like it. All right, so what are you guys' thoughts? Let's start with which one is 0.
Yeah, 0 would be E.
Yes. So 0 is going to be point E, and we know that just because it's right here on the top. It's going to be, later on, we're going to call this a maximum, where the derivative is going to be equal to 0. Right now, all you guys need to know is that the slope here, the tangent line to the curve, looks like that. I have a tendency to also draw lines because instantaneous rate of change can also be kind of expressed as the slope of the tangent line. So I'll just draw a quick line by that point that goes right through that point and see what it looks like. And here we've got a straight line. All right. Which ones are negative? We've got 1 at -1 and 1 at -3. So
C and F are both negative?
C and F are both negative. Which one is the slope of -3 and which one is the slope of -1?
F looks like -3.
Yes. So if I sketch out my little line thing here going at F, and then I compare it to my line that I would draw here at C, I can see that this is a very steep slope and this is not a very steep slope. So if F is going to be more negative than C, we can confidently say that that is going to be -3. And this one is going to be 3. Or, excuse me, -1. Sorry. All right. So I have 3 more points. I have 1/2, 1, and 2. Which is number 2? Which has the greatest slope?
To me, it looks like B.
That's...
I'm sorry, correction, D.
Yeah, D is going to be correct. So we draw that line, and we can compare it to the line that we're going to draw here for B. This is just kind of like a greater, like we were kind of sketch out a triangle here. It would be, you can kind of see that there's more rise over run than for B at this point. And finally, that leaves us with A, being our 1/2. And it is less of a slope than b, so that makes sense. All right. Any questions about how this went down?
No, not really.
Sweet. Let's go ahead and move on to do some problems from 2.2, which is the derivative function. All right. So, do you guys have any questions about this chapter or this section in particular? We're going to try to do some of the drawing ones. I'm not entirely sure how many of these you would have on an exam because you guys take your exams online. But I remember this being a huge thing in my classes, and the reason is it kind of allows you to like visualize the derivatives very well. So we're going to be in 2.2, page 101. We're going to start with problem 2 and problem 4. Okay, so we are going to be graphing some derivatives. Of some functions. So this first one looks like we have something that looks like this. What can you tell me about the equation for this? You don't have to tell me the exact equation, but what type of a function is this?
Would it be exponential decay? No.
It's not going to be exponential decay. Exponential decay is going to look something like that.
Okay.
This is a parabola.
Okay, that's what.
Yep. I can get my eraser to go. So the equation that this would be kind of related to is y is equal to x squared, which would look like this. So basically the only difference between this one and this one is some, like, you're like stretching it, you're moving it up, and you're flipping it over. But the point is that this is a parabola, and we know that there's going to be an x squared in the equation for this graph, which will become relevant in just a few minutes. Okay, so let's graph this derivative. What is the first thing I should do when graphing a derivative?
Find the zeros.
Yep. So I have this 0 right here at 1, 3. I know the slope here is going to be 0, so that means my derivative at x is equal to 1 is going to be 0. What about before that? Let's separate it and look at this chunk. Is my slope going to be positive or negative here? Positive, yep. So I know that I'm going to be looking in this direction. This is where this orange chunk will be. And then here, my slope is going to be negative. It's going down. So this is going to be in this chunk. All right. So now the question is, does it start off? Let me think about how to best phrase this. If I were to put 2 points, here is A and here is B, which would have the more positive slope?
B.
Yes, B. So what's happening here is that it's going from a more positive slope to a less positive slope. It's approaching 0. So what it's going to look like is this. And it's going to be the exact reverse, going from x is equal to 1 on down, because it's starting off not very negative and becomes more negative. So this is what the graph of the derivative is going to look like. That being said, we also know that if y is equal to x squared, the derivative of this, which you're going to find out in like the next chapter, I think, but it's just kind of something that I always keep in my back pocket when I'm sketching these types of derivatives, is that the derivative of y, which we're just going to call y prime right now, the derivative, is going to be equal to some function of x. So if it's just a regular old parabola, it's going to be 2x. In this case, because it's not a regular old parabola, these are not the exact equations, but the idea is that we go from an x squared function, this is a parabola function, we take a derivative, and now we have a function that is linear. And I'm going to go ahead and tell you right now, if you have a cubic function, a function that looks like this, and you take the derivative of this, the function is going to be a parabola. You're always taking it from higher power to lower power, which is going to become, you don't need to know this for an exam or anything. If that helps you when you're thinking about sketching graphs, then good. If you don't want to think about it right now, then that is also a-okay. But
thanks for that. Yeah,
no, it's just something that helps me when I think about this. So I always know that I can't have something weird going on here. It's just going to be a line. Okay, let's take a look at number 4. Periodic functions, good times. I want to get this to look about right. So I think that looks approximately right. All right, so this is like, what, 1.5? I'm sure the answer to this is actually in like, you know, like pi and stuff like that, but I don't really want to think about that right now, so I'm just going to go for it like this. So that would be a peak at about, I don't know, it's just above 1, so yeah. Okay, so I've kind of sketched that out. I found some important spots in this function. This is ending cutting off at 4, and I don't really do a very good job of scaling it. I'm sorry. -4. My scaling is not always the best. Okay, so let's graph this derivative. First of all, we're going to track down some zeros. Where are my zeros hanging out? They're going to be right here. Ooh, I still have a line on. That's not going to be very useful. Yep. So I'm calling this about 1.5 and -1.5. That's actually a little too far that direction. Okay. So now I'm going to identify which chunks are going to be positive and which chunks are going to be negative. What about this side of 0? What is this going to be? Is this positive or negatively sloped?
Negative.
Yep. Now I'm going to look at this middle chunk here, and because there's no 0 in the middle breaking it up, we can just do it as one whole shenanigan. So this is going to be positive. And here at the end, it's going to go back to negative. So I know that this chunk is all going to be up in this positive region, right? Because this is our positive area, and this is our negative area. I did not color code that correctly. I'm going to use the colors. I might want to keep it correct. All right, so that's our positive. and this is negative. And we're going to have negative areas from here to here. And we're going to have negative from here to here. And that's going to be in this. I also drew a positive down here. I'm such a fool. Okay. All right. So where is it the most positive? Or rather, if I were to have something right here and say that that's point A, and then something here that is point B, and then something up here that is point C, where is the most positive of them all?
B.
B, you're right. So it looks like it goes from kind of positive, little positive, baby positive, all the way up to as positive as it gets at about B, or rather right here is kind of where that point is, where it's the most positive. It's right in the middle of these two. And since I drew it as negative 0.5, 1.5, and 1.5, I'm just going to call it right at 0, where my most positive is. So I'm going to peak, and then it becomes less positive from there. Still positive, but it's getting less so as it's approaching 0. So I have something that looks like that. Okay, what about here? If I have a point here and a point here, this is how I kind of think about a problem like this. I'm going to say which one is more positive than which. D is going to be, or more negative in this point, D in this case is going to be less negative than E. I would sketch out my lines that kind of look like this. That's a little dramatic. So D is less negative than E, so I can assume that it's going less negative, or going more negative as my x-axis becomes more negative. And that is the same case here. We have tiny negative, baby negative, just a little negative, and then it gets to be very negative. What is happening here, though? This is very negative. The way that this is drawn, never mind. The way that this is drawn, this is just the way that we're going to do it. I'm going to go right down like that. Yeah, theoretically, this graph is going to continue on. It's going to do something that looks like this. Therefore, at about this point, we would stop getting more negative and start getting less negative. So our derivative would start to turn back up, and at whatever point this is, it would hit 0 again. So we're going to call that just point G. So x is equal to G, and this is also x is equal to G. So that is 0 point. Does that make sense? So the stuff in the blue is just stuff that I'm extrapolating from my knowledge of this being a periodic function, but that's not actually given in the graph of number 4. Okay. All right. Any questions about what happened here, graphing these derivatives?
No.
Sweet. Let's do a couple more from this section. Let's do this section is a lot of drawing. Let's do a couple of 18 through 21. Let's just do 18 through 21. This is a matching one. So this is on page 102, and we're doing 18 through 21. So each of these functions, there's a huge chunk of derivatives. There are 8 derivative functions, and there are 4 functions that we're going to be looking at. And let's just match them up. So 18, 19, 20. All right, which of these do you think is the derivative of 18? First things first, what I see when I look at this is it's probably a cubic function. So my brain is going, look for a parabola, because if I'm going to take a derivative, it's probably going to be a parabola. I can show that using this graph by saying, hey, I have, that's not a dramatic color, like I thought it was. I have a 0 here and a 0 here. So in this sketch I'm going to kind of do of this new function, I'm going to have 2 zeros. And then I'm going to go ahead and say this chunk is positive, right? This is where it's the most positive, right here. And then both of these are negative as x is getting larger. Do we have one of these matching that looks like this?
Yes. That was number 8?
Yep. So this is going to be number 8. All right. What about 19? Is the slope of this changing at all?
No.
No. It's going to be some number. We could calculate what number it is if we wanted to, probably. Let's say it's like -2. The slope of this is -2. It's going to be -2, or it looks closer to -3, -3.5, something like that. It's going to be that the whole time, because this line is going from, if we have x, and we take its derivative, we're just going to get some number. So that's exactly what happens here. We're going to end up with a function f prime of x is equal to some number, which is going to be a flat line, which is going to be number 4. And we know that number 4 makes sense because it is negative and the slope of 19 is also negative. Okay. Let's take a quick look at 20 and 21. Here we have a parabola. So what am I going to be looking for in terms of a derivative?
A straight line?
It is going to be linear, yes. It's not going to be a flat line like we had in the last one. It's just going to be, I'm trying to make this not wobbly, but I don't know if that's possible. So we have a couple of lines here. We have 2 lines. We have line number 2 and line number 7. Which line do you think is associated with number 20? First thing first, I will figure out what the 0 is. So what I would do is I would say here I have line number 7. And here I have line number 2. Or, yeah, 2. This is number 2. And this in the peach is number 7. Number 2 is the one that has the 0 that is in the positive region. If we were to draw a parabola with number 7, it would have to be over here, where that peak is here in the negative region. So there's where my 0 is. Derivative is equal to 0. So what I'm looking at is number 2, not number 7.
Okay. That was a great explanation. Thank you.
Yeah, no problem. All right. So finally, we have number 21, and it looks kind of like a disaster. So let's just break it down into parts that we can work with. I'm going to draw straight lines, I swear. See, that doesn't look miserable. Okay. All right. So we have this, and then it peaks and comes down and goes like that. All right. So where's our 0? It's going to be right here at this little hump right there. So I know we have f of, this is f prime of x, f of x. So this is where f prime of x is equal to 0 at this x value. What about this chunk when x is more negative than that? This is a little positive, more positive, more positive, and it gets more positive the more negative we go. So very, very positive, approaching not so positive. So it'll look something like that. All right. So then we have this section here that is kind of negative. And then instead of getting to be more and more negative, what it is doing is it kind of gets a little negative, and then it comes back, and the slope of this is negative but approaching 0. Right? Because theoretically this is going to go on forever, and it's going to get very, 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 very close to 0. It's going to be like a million, like 0.00000 on for like essentially infinity. But it's not going to actually be 0, because at the end of all of those zeros, it's going to be like 1 float. It's not going to technically be 0. So it's going to approach 0, but not actually equal 0. So I'm going to kind of draw it in that, I'm going to draw it in like my 0 red, but just a little bit off of the axis. So this, yeah. This point is kind of the point where it goes from being more negative to less negative, and so it's going to kind of look like this. All right, so basically the strategy to tackling any of these is figuring out where your zeros are, and then breaking it into where is my slope getting bigger and where is it getting smaller. And doing that kind of let us figure out that it's not going to be 1, it's not going to be 3, it's not going to be 5, it's going to be 6. So the answer to 21 is going to be 6. Even though 5 would kind of look like a very tempting answer. All right, any questions?
No, not really.
Sweet. Let's do a couple problems from 2.3 then. All right, let's start with sorry. Okay. Okay, let's start with 2.3. We're gonna do problem 2. I am on page 108. I'm going to start with problem 2. So here we're kind of relating, we are relating the like meaning of the derivative to the math. So it's kind of like being when you're given a word problem and you're asked to like fish out all of the details from it. So we're asked to write the Leibniz notation for the derivative of the function and include the units. So we have a cost C of a steak in dollars is a function weight W of the steak in pounds. So first things first, I can just write C cost is a function of W. I'm just gonna like that. And then the function can look something, it could be linear, it could be like 3W plus 4. Like, it doesn't matter really right now what this is. It could be some extremely complicated polynomial that nobody wants to touch. The point is that the function is cost is dependent on weight. Can everybody get behind me in deciding that this is the function we're going to use?
Excuse me?
Yes.
Oh, I thought you were asking a question. I never heard you.
Oh, sorry. I was just kind of asking, like, everyone can get behind this as what the function that we're going to use.
Yes.
Okay. Because sometimes it can be a struggle for students to figure out what exactly is the function that they want to be working with. So now we're going to write in Leibniz notation the derivative of this given function. So that is going to be, Leibniz notation is what we learned at the beginning of this section. And we're going to use f prime a lot in this, but in this like whole class. But Leibniz notation here is going to be, we're saying we're taking, this is the derivative is going to be the derivative of C with respect to W. So another way we could write this is C prime of W. And they both essentially mean the same thing. This is just a more, this stuff in the pink here is a more clear way of explicitly stating what we did. Okay. Does that make sense? How, I don't know, did that, picked out that function?
Yeah.
What about number 4? Here we have pay in dollars as a function of hours worked in times, or in time. So we have pay as a function of hours. So the more hours you work, theoretically, the higher your pay is going to be. We don't know the function, so I guess we can't actually say that, but we do know that pay is dependent on hours. All right, so we're just going to say this is a derivative of pay with respect to hours. And this is going to be P prime of H. One thing that I think is important to like state right now is that this is not a fraction. And it might be tempting for you to treat it like a fraction, but for your sake right now, just think about this as one whole unit. This is like meaning derivative right now. So yeah. It cannot be split up at this point in time. Yeah, it's a rough like way. They never explicitly state it, and they absolutely should, that this is not a fraction. You can't treat it like a fraction. I did that too. And sometimes there'll be like shortcuts, like very later on in your calculus career, where they will split it up and they'll do random stuff with it. And it is a shortcut. Like, if you do the whole proof, You're not like splitting it up in that way. But for all intents and purposes right now, don't think of Leibniz notation as a function. Because it's one whole thing. And I've probably said this like a million times, but I'm just going to reiterate it. You kind of read it from top to bottom. So this is the derivative of pay with respect to how many hours worked. So how does the pay change based upon how many hours worked? Okay. So that was kind of that, a little bit of fundamental stuff. All right, let's do number 8. And then all right. So we have this graph here. And it wants you to estimate the derivative of sorry, I'm so sorry. Okay, so it wants you to estimate the derivative of this function at x or t is equal to 6. This is actually, I don't want to do this problem. This is a lot of busy work. Your approach to solving this problem should be what you would do is you would say, hey, I'm going to find out what f of 6 is, and we kind of did this at the very beginning. Or in order to estimate it, what we would do is find f of 8, f of 7, get closer, and we probably wouldn't need f of 8, that would be funny. We'd want f of 5, and we would compare the average rates of change and see what they're converging on. So we would say f of 6 is equal to 140. F of 7 is equal to, I don't know, what is that, 170? F of 5 is equal to 120. And so we would use this, and then we'd find f of, or we'd estimate f of 7 point, or 6.5. And we'd get closer and closer and closer until we saw what it was converging on. So that is how I would suggest estimating f prime of 6. But I don't really want to do all of that math right now, and we already did it today. So let's do another problem. Let's do 18 instead. So let G be the annual U.S. government purchases, T be the annual U.S. tax revenues, and Y be the annual U.S. output of all goods and services. All three quantities are given in dollars. Interpret the statements about the two derivatives called fiscal policy multipliers. So basically, it's asking you guys to explain what this means. Oh, that probably needs to equal something. All right, so this first one, we're going to say it's about the rate of change of Y, which is U.S. output of goods with respect to government purchases. And what we're saying here is that Y is going to be a function of G. So this is output of all goods and services. I don't really understand how the government works, so I'm not sure if that entirely logically makes sense, but mathematically, that's what it's got to be. So there is a function y of g, and when you find the derivative of that, it's going to equal 0.16. That being said, the rate of change of U.S. output of goods with respect to the government purchases is positive. So theoretically, if government purchases were to go up, then the output of goods would go up as well. So if we kind of have a graph, and again, I'm kind of making up all of this information so that I can kind of get a graph going, because I don't really have much to go on. But I'm going to call this y, I'm going to call this g, and I'm going to say that if g increases, then y also increases, meaning that I have a positive rate of change. And that's why we really care about here, that this is positive. Okay. Does somebody want to explain the next one to me?
The rate of change will be the U.S. output of goods with respect to the U.S. tax revenues.
Okay, so there is a function somewhere y of t, and this is going to be y prime of t, and it's negative. So what does that mean?
That means the graph will be, the function will be decreasing.
Yep. So as t increases, y is going to go down. So we're going to have a negative rate of change. And again, I have no reason to assume that the functions look exactly like I drew them, but I drew them that way to better visualize what's actually happening here. And what is happening is that this is negative, and so has a negative relationship, a negative rate of change. As tax revenue increases, U.S. output of goods and services decreases at a rate of negative 0.26. But we don't really need to know the rate. Again, I don't know anything about government, so I don't know if that is a reasonable thing to say or not. But that's what the math is telling us. Okay. Does anyone have any questions about any of this stuff? Derivatives, rate of change, drawing graphs?
No, not really.
Okay. In that case, I'm probably going to sign off and let you guys go at it.
All right, thank you so much. I really appreciate it.
Yeah, of course. You guys all have a great night.
You too.
Bye.